You know that feeling when you're in a super crowded room and everyone's talking at once? It's just chaos, right? A wall of noise. Well, believe it or not, our wireless devices are in that exact situation every single second. So today, we're going to pull back the curtain on one of the coolest solutions to that chaos: Space-to-Vision Multiple Access, or SDMA for short.
So here's the game plan. First, we'll talk about the basic challenge of sharing signals. Then, we'll dive right into the nitty-gritty of how SDMA actually works its magic. After that, we'll see how it makes networks way more efficient, where you can find it in the real world today, and finally, we'll see how it stacks up against some of the other methods out there.
Okay, let's jump back to that crowded room analogy. In the world of wireless, that room is basically a frequency channel, and all of our phones, laptops, and watches are the people trying to have a conversation. If they all just shout at the same time, well, you get nothing but static, a total mess.
And that leads us to the fundamental question that engineers have been wrestling with for decades. How in the world do you get all these different devices to communicate clearly and efficiently all at the same time without just screaming over each other?
Well, the answer that SDMA gives us is actually kind of brilliant in its simplicity. What if, instead of making everyone take turns talking or giving them all a secret code word, you just had them stand in different parts of the room? And that's pretty much what SDMA does. It separates users based on nothing more than their physical location in space.
All right, so how does a network actually separate users in physical space? I mean, it sounds like science fiction, but it's not magic. It's just some really clever engineering. Let's get into the core mechanics of how this all comes together.
The secret sauce behind SDMA really boils down to a few key ingredients. We're going to look at 3 of the big ones: beamforming, spatial signatures, and something called cell sectorization.
So let's start with beamforming. Picture a cell tower using its smart antennas to send a super-focused beam of data, like a laser pointer, directly to your phone. This means it's not blasting the signal everywhere and bothering other people. At the same time, the system could identify each user's unique spatial signature. That's the one-of-a-kind path the signal takes to reach you. This helps tell your signal apart from everyone else's. And this is all happening in what's called a multi-user MIMO system, which is really just a fancy way of saying lots of antennas are serving lots of users all at the very same time.
Now, the other big technique is cell sectorization. Think of a cell tower's coverage area like a giant pizza. Sectorization just cuts that pizza into smaller slices. Each one of those slices, or sectors, gets its own dedicated directional antenna, so it only has to worry about the users inside that one slice. This is huge because it means the system can reuse the exact same frequency in different sectors, which just massively boosts the network's capacity.
Okay, so we know how it works, but what's the big deal? Why is this so much better? Let's talk about how all this tech adds up to a network that's way more efficient, with a lot less noise and a much stronger signal for everybody.
You know, the #1 enemy of any wireless signal is interference, and SDMA comes at this problem with a really powerful 1-2 punch. First, like we just saw, there's beamforming, creating those focused, narrow beams. But the second punch is something called spatial filtering, and this is where it gets really smart. The system uses these advanced algorithms to actively listen for and block out signals coming from directions it doesn't want. It's kind of like giving the receiver a pair of high-tech noise-canceling headphones to tune out all the extra chatter.
And this really gets to the heart of the whole concept. It's the difference between using a giant floodlight that just illuminates an entire field versus using a laser pointer that hits one specific spot. By focusing all that signal energy only where it needs to go, SDMA wastes less power and, crucially, creates way less interference for everyone else.
But here's the part that makes it truly powerful. This whole system isn't static, it's alive. If you walk from one side of a room to the other, the SDMA system sees that and adapts. It can literally steer its beams and adjust to new conditions on the fly, in real time. It's this dynamic adaptability that makes it so perfect for our constantly moving, changing world.
Now, this all sounds pretty amazing in theory, right? But this is not science fiction. This technology is already out there, all around us, powering the very systems we rely on every single day. So the big question is, where do we actually see this stuff making a difference? Well, some of the answers might just surprise you.
The biggest, most important application right now? 5G. Let's be totally clear. The insane speeds and capacity that 5G promises, they would be completely impossible without SDMA. 5G networks use a technology called massive MIMO, where a single base station might have hundreds of tiny antennas. How do they keep all those signals from turning into a chaotic mess? You guessed it, SDMA. It directs these incredibly precise individual beams to tons of users all at once. This is exactly how thousands of people in a packed football stadium or a busy city center can all be streaming high-def video at the same time.
But it absolutely does not stop with 5G. Think bigger, like way bigger. Satellites orbiting the Earth use SDMA with these powerful directional antennas to beam down internet service to completely different countries from space. And then, back on the ground, self-driving cars rely on it for that critical, real-time data exchange they need to see the world around them. Even the smart building you might work in is using SDMA-powered Wi-Fi to handle all the IoT devices, the thermostats, the security cameras, the smart lights, all chattering away at once without clogging up the network. So to really appreciate what makes SDMA so special, it really helps to put it side by side with the other ways engineers have tried to solve this crowded room problem over the years.
Okay, let's take a look at this first comparison. Just focus on that very first row, separation method. This is everything. You see TDMA? It slices up the channel by time. Basically, everyone takes a turn. Then you have CDMA, which uses unique codes. It's like everyone's speaking a different language. But then look at SDMA. Its method is purely based on physical space, and that changes the whole game. It allows for continuous transmission, and if you look down at interference handling, you'll see it just filters out interference spatially, instead of needing these awkward guard times like TDMA.
Now, on this next table, let's look at the advantages for SDMA. The two huge wins are high capacity and something called spatial reuse. That means we can use the same frequencies over and over again as long as they're in different locations. Now, the trade-off, as you can see under disadvantages, is that you need these more complicated smart directional antennas. And that's exactly why you see SDMA in cutting-edge systems like 5G and modern Wi-Fi, while the older methods are often found in legacy systems.
So, when you boil it all down, SDMA solves that classic crowded channel problem by treating physical space itself as a resource to be managed. And as we keep packing more and more devices into our world, from our pockets to our cars to our homes, you have to wonder, is the ultimate solution for our data-hungry world not just finding more channels, but being way smarter about the space we already have? It's definitely looking like one of our most powerful tools. What do you think?